In this video, we are going to study the detail of the states and the regions that the substance undergoes as energy is being added into that substance. We are going to use the temperature and volume diagram for this. So recall that in this temperature volume diagram, we have the saturation curve. So that refers to this bell curve here shown in black, and on top of it, it's there's a point here called the critical point. So um, anything to the left of this point and along this line here, along this saturation line, that's gonna be or that is called the saturated. So this is called the saturated liquid line, and anywhere to the right of this critical point but still along this curve here, this is what we call the saturated vapor line. And when we say saturated, basically it just means that it's fully it's let's say it's fully liquid here, in the sense that if we compare this point here to this point on the other side, the saturated vapor, that means at this point this is fully liquid. That means there's no vapor yet, there's no vapor phase at this point. But then if you go to this point on the right, that's going to be fully vapor. That means no more liquid on this point. And that means that anywhere in between, it's going to be a saturated mixture. So some portion of the substance is still in liquid phase, and other portion is already in its vapor phase. Okay, so the region inside the curve is what we call the saturated mixture, and the region outside this saturated liquid line, is the liquid region. And to the right of this, or to the right of this saturated line or saturated vapor line, is the superheated region. Okay, so we'll be using water for this discussion, and then we will take initially at 25 degrees C, and the atmospheric line, by the way. So here's our atmospheric line, sorry, pressure line. So pressure line, that means taken at 1 atmosphere. So this is a constant pressure line. So that means that at 1 atmosphere, it is known that the boiling point of water is at 100 degrees C. Then the freezing point is at 0 degrees C at 1 atmosphere, or at sea level pressure conditions. So that means that if the pressure is no longer 1 atmosphere, so say we increase the pressure, that means that this boiling point right here will also increase. And if we reduce the pressure, that means the boiling here will also reduce. Okay, so that's the reason why that at higher locations, far from the sea level heights, then the boiling of water does not reach 100 degrees C anymore. So it's because that the pressure is actually lower at mountain regions. So that's it, and we have here our illustration. So again, we are going to consider 25 degrees C, and at 25 degrees C, the state of the water is actually at liquid. So we are going to add heat so that we change it from this point here to this point here, to this point S. Okay, so in the liquid region, we are here, say 25 degrees C. So as we add heat, then the temperature will actually rise until it gets to this point, saturated liquid point F. So it's fully liquid, but still, it's 100 degrees C, but it's in fully liquid condition. So from here to this point there's going to be a change of phase that will happen, and that change of phase occurs at the constant temperature, which is 100 degrees C, or the saturation temperature. Okay, so in this phase now, this is what we call the liquid vapor region. So that means some portion of the substance is in liquid while the other portion is in vapor. So right here, this point, we use the subscript F, and then at this point, saturated vapor, we use the symbol G. So anywhere in between is going to be a mixture. So we will introduce another property called the quality, or the letter X, the quality. So that means at point F, that means because the definition of this quality is the mass, or how much water vapor, or mass of water vapor is in this substance. So mass of water vapor divided by the total mass of the substance. So when I say total mass, that means that's the sum of the mass of the liquid and the mass of the vapor, so total mass. So that means that the X value here, or the quality at point F, or at saturated liquid, is equal to 0. And then at point G, the quality of the water vapor is 100, or if it's not in terms of percent, then it's just 1. Right, so this is 100%. That means that all substance is in vapor state already, and in between is going to be a mixture, as I've said. So therefore, the range of this quality is between 0 and 100. So let's say we are now in this saturated vapor point, and further heating will cause this point to change temperature. So as you see here, there's going to be a change in the temperature, and the state of the substance is going to be the superheated. This is called superheated steam. So that is now the superheated state. So that is beyond the saturation curve already. So now, where are we going to get the data for the properties? So there's actually various ways that we can retrieve the data. So one is through the use of tables, available tables for common substances like water, for example, or refrigerants. So there are tables already, and we can also have graphs, we can also have equations and computer softwares, direct experiment measures, and maybe some other else. But in our course here, or specifically in this topic, we will use the tables. So the tables will be using one of our reference texts, The Fundamentals of Thermodynamics by Sontag, Bordnak, and Van Wylen. So at the appendix, there's this table, appendix B. There's table for various pure substances, appendix B. Okay, so just in summary, here's the table. So we have table for water, so that's for B.1, and B.2 is for ammonia. That's a type of refrigerants. Actually here they are refrigerants. And then table B.3, that's for R12, and B.4 is R22, and B.5 is R134A. So there are types of refrigerants. And then B.6 is for nitrogen and methane. So even if it's just for water, there's subtables here, B.1.1, and all the way to B.1.4 to 1.5. So each table actually corresponds to the regions in the diagram. So say in this B.1.1, it refers to saturated water or liquid vapor. So in that mixture, anywhere in between, So right here in between. So saturated water, liquid vapor, and the entry is temperature. Okay, and for table B.1.2, it's actually the same saturated water, liquid vapor, but the entry is pressure instead of temperature. Our entry, let's say our available data, let's say from a given problem, it's given in terms of pressure rather than temperature. So we will use this table B.1.2. And then for B.1.3, it's for superheated vapor. That means it's for this condition. Then compressed liquid, that means it's for this condition. Then there's also saturated solid, saturated vapor, water. So it's just additional tables for the water. But for the refrigerants, you will notice that it's only the available data is for saturated and superheated. So here in R12 we have saturated, superheated. For R22, saturated and superheated. So it's just the available tables that's given here is saturated and superheated. So now let's go to our tables. So here's our thermodynamic tables that we'll be using in this course, taken from one of our reference texts. This is the appendix B of that text, and for SI units. So right here I have also included the bookmarks for the specific tables. So say B.1.1, that's the saturated water, liquid vapor, and the entry is temperature. And for B.1.2, it's somehow the same as this, the saturated water in B.1.1, except that the entry is pressure. So you see here the first column is in temperature, and the second table is, the first column is in pressure. So that's the difference only. Then for B.1.3, it's superheated water vapor. Then B.1.4, compressed liquid, and B.1.5, it's saturated solid, saturated vapor water. So I think we're going to hardly use this. I mean, not much that we're going to use this. So probably most of the tables that we'll be using when, let's say, the substance water is the B.1.1 and 0.1.2 and 0.1.3. Okay, and then at B.2 onwards, it's for refrigerants. So B.2 is ammonia. We have saturated ammonia, and here superheated ammonia. Then the B.3.1 is saturated R12 and superheated R12 for the next. Then here, so starting from the ammonia, we only have saturated tables and superheated tables. So now let's go to this table, saturated water table, liquid vapor, and let's have an overview of what's inside this table. Okay, so first column here is the temperature. So temperature meaning that the entry here is the temperature, and then the next column is the pressure in kilopascals. So temperature is in degrees Celsius and pressure is in kilopascals. And it says here saturated water. That means that if here's our saturation curve, that means that the so here's our points here. So we have this saturated liquid, and here is the saturated vapor. And recall that our subscript at this point is F, and here is G, and anywhere in between it's FG. So here's our properties. We have a specific volume in cubic meter per kilogram, and then internal energy in kilojoules per kilogram. And for each of this property, we have V sub F, let's say specific volume at F. That means that's the specific volume at point F. And then at point G, that means the specific volume at that saturated vapor point. And anywhere in between, or actually it's not anywhere in between, but corresponding to this entire volume change here, that's going to be Fg. So again, it's not the anywhere in between, but rather the Fg corresponds to the entire volume change from point F to point G. So it's the same with this internal energy. We have UF, UG, and anywhere in between, the change between these 2 points is the UFG. Right, so you see 2375 minus 0, so it's this one. Okay, so next page is, because in this page we only have specific volume internal energy, and if you check the second page, we have actually the same temperature and pressure. So this is 0.01, 5, and 10. You check here, it's the same 0.01, 5, and 10, but the properties is different. So we have enthalpy and entropy. It's still the same that we have the subscript F, G, and Fg. For entropy, we have SF, Sg, and SFg. The units, by the way, for this enthalpy is kilojoules per kilogram, and for entropy we have kilojoules per kilogram Kelvin. So we have this temperature included here. So again, when you say Fg, that means that that's the enthalpy that is needed to bring this substance from point F to point G. So that's a specific is a specific property, so kilojoules per kilogram. So that is the amount of energy or enthalpy that is needed to change the phase from saturated liquid to saturated vapor. Okay, so next one is the table B.1.2. So as I've said, it's entirely the same except for the data entry. So instead of having a temperature in this first column, we have pressure in kPa instead. So here's the pressure column, this is the pressure entry, and the properties here are the same. We have specific volume, internal energy, and in the next page it's still the same, but the properties are enthalpy and entropy. Okay, so next one is the superheated vapor. So the superheated vapor is, if you recall our DV diagram, so let's say here's our saturated mixture line, and here's our superheated line. So it refers to this point right here. So that is why you don't see no subscript anymore. There is no VF or VG or VFG because we are in this superheated region. So you see here we have temperature in the first column. So temperature in the first column, and we have this first set, as you can see. So for this temperature, what's the volume, specific volume, internal energy, enthalpy, and the entropy. And another set here, volume, specific volume, internal energy, enthalpy, and entropy. But you will notice that there's a difference in the pressure. So even we have the saturation temperature, that is true for that is true for the entire line, but the pressure is actually different. So one corresponds to 10 kPa, the other one corresponds to 50 kPa. So you see here that the saturation temperature starts with 50, 100, 150. So I think the interval is by 50, 200, 250, 300, and then here 400, the interval is by 100 already. But then at this another set, we have 100 kPa, for the pressure and 200 kPa for the pressure. You can see that the saturation temperature again goes back to 150. So it goes back to 150, 200, 250. So instead of starting at 50, it just started at this 150. But the point here is that it goes back to some lower value. So it does not continue to 1400. Okay, so that's the superheated vapor. And there is this inside term in this, inside of these groupings or parentheses, we have 45.81, and that actually corresponds to the I think saturation temperature for this pressure condition. So say for this temperature kPa, the saturation temperature would be 45.81. Since the saturation temperature is higher, 50 is greater than 45, that means we are in the superheated region. Okay, so again, this term here inside this parenthesis, this corresponds to the temperature, saturation temperature. That means it's here. So this is Tsat at this pressure value. So if we have higher temperature value at this pressure, that means we are in the superheated. So that is the meaning of all this. Then we also have compressed liquids. Again, you will see there is no subscript F, Fg, and H. It's just simply because we are not in the saturated mixture region, but rather we are here, somewhere here. So that is why we only have one value for V, U, H, and S, and here V, U, H, and S. So same saturation temperature, and we have this pressure. So almost the same like the superheated vapor. And you will notice that for refrigerants, there's no available or attached data for the compressed liquid compressed liquid refrigerants. So that means we have to use maybe approximations for this if we need the data for the compressed liquid. Okay, so I think that's all for this thermodynamic tables, and now let's go back to our presentation. Okay, so now that we have seen the property tables already, then we have seen that the values are at some intervals. But sometimes when we're doing the problems, we can encounter that the values that we are finding does not fall actually on the grid values, but rather on somewhere in between. Like for example, we have this table values at 0.1 and 0.2. So the blue box here corresponds to some table values. That means we obtain this data from from the table, and we are going to find the value in between. So here is the, let's say the 215 that's the given value, or our or that's what is given in the problem, given in the problem, and we are asked to solve for this volume here at this temperature. So what's going to be the volume at this temperature? But the table only has this value 200 and 0.2, and here 240 and 0.2275. But what if we need this value in between? So to do that, we need to use the interpolation. So the idea is that, let's say here's the table value. So it has a volume and it has a temperature, and at another point, at some interval, we have this another volume here and another temperature. And what we're looking so happened that it's somewhere in between. And this interpolation, that means we assume it's linear. So to do that, actually, we we just use this. So first is this value right here in between minus the 0.1 all over, or let me write it here. So 215 minus 200, right? All over 0.2 minus 0.1. So 240 minus 0.1 is equal to, so the middle value minus the 0.1. So V minus 0. 0.2060 all over 0.2 of the V value, 0.2275 minus 0.2060. So in this equation, this is one unknown, so therefore we can solve for the V. So this is called the interpolation. Okay, next one is it says here another reference that is also useful for steam tables. That means the substance here is as water. This is useful because, as you can see, that the temperature intervals here, we have let's say we have 1, 2, 3, 4, then 5. So instead of a bigger steps, we have a smaller intervals, which means that the probability of doing a lot of interpolations would be lessened because we have a smaller intervals here. So that is the advantage of this reference steam tables. But again, the downside is that this is only for water substance. So if the substance, the problem is not water anymore, then that means we cannot use this table. Okay, and the next one is the approximations for liquids. So although we have seen already that for B.1.4, I think we have data for the compressed liquids for water only, but for other substances like the refrigerants, we only have saturated mixture and superheated vapor. So that means we cannot use, or if we don't have those tables, that means we cannot we need another way to be able to retrieve the data for the liquid conditions. So one way is to approximate. We use this approximation for liquids. So that means that at here's our saturated liquid line here. Here's the saturated liquid line, and here's the dashed line is the constant pressure line. So P is equal to C. So somehow we can say that, let's say we want to find this, but in order to find this, we just approximate that the specific volume at this is just simply the specific volume at saturated liquid at this temperature. Okay, so it's just an approximation. So again, the volume or the properties that we want, let's say specific volume or internal energy or enthalpy, we can approximate that if we are in the compressed liquid region only. So if you are in compressed liquid region, then we can approximate this value here for V, for U, for H, that this value will corresponds to this value. That's the value of the property at the saturated liquid point at this evaluated at this temperature. So it's not the temperature here, but rather at this temperature. So it's almost the same. So that is an approximation. Okay, so I think that's the end of our lecture. Then in the next video, we are going to do a couple of sample problems regarding this reading the thermodynamic property tables.